Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be discussing about rotational and vibrational Raman spectra under the paper Atomic, Molecular and Laser Spectroscopy. After going through this, we will be able to learn about Raman scattering, rotational Raman spectra, vibrational Raman spectra, vibrational rotational Raman spectra, intensity alteration in Raman spectra, and infrared spectroscopy. Infrared and Raman spectroscopy, the difference between these, Raman and IR active modes for carbon dioxide molecule, difference between IR spectra and Raman spectra. Raman spectroscopy is concerned with radiation scattering from a sample. This scattering occurs when an incident photon interacts with the electric dipole of a molecule. This scattering process can be either elastic or inelastic. Most incident photons are elastically scattered by the molecule, and we refer it to the Rayleigh scattering. In Rayleigh scattering, the energy of the incident photons equals the energy of the scattered photons. A small fraction of light is scattered at energies different than that of the incident photons and is referred to Raman effect. The Raman effect is an inelastic process. The two situations arising with Raman scattering are: scattered photons have a lower energy and referred to Stokes scattering, and the scattered photons have a higher energy and we refer it to the anti-Stokes scattering. The energy of a vibrational mode depends on the molecule's structure and environment. Raman spectra of different molecules are unique. Raman intensity lines are 0.001% at the most of the source intensity. The intensity can be increased by 10 to the power 3 to 10 to the power 6 orders of magnitude if the sample is adsorbed on the surface of colloidal metal particles. Rotational Raman spectra. We know that Fj is equal to Bj plus 1 minus D j square j plus 1 square, where j is equal to 0, 1, 2 up to D is the centrifugal distortion constant and is ignored in Raman spectroscopy due to the presence of the measurements, because the measurements are quite precise. One can neglect the distortion constant. Therefore, retaining only the first term, the rotational energy levels are Fj is equal to Bj j plus 1. Delta j is equal to 0 plus minus 2 are the selection rules for the transition between rotational levels in Raman spectroscopy. There is a change of 2 units in the rotational quantum number that is connected with the symmetry of polarizability ellipsoid. The ellipsoid presents the same appearance after pi radians during end over end rotation in case of a diatomic molecule. The magnitude of the frequency shift is given by delta nu is equal to f j plus 2 minus fj is equal to b j plus 2 j plus 3 minus bj j plus 1 is equal to 4b j plus 3 by 2. The figure here depicts the transitions between rotational energy levels. The selection rules dictate a series of equally spaced Raman lines on either side of the undisplaced line. The two series of lines are called S branches and both have j is equal to 2. The transition j to j plus 2 results in a shift to longer wavelengths and are referred to Stokes lines, while transitions j plus 2 to j results in a shift towards shorter wavelengths referred to anti-Stokes lines. The separation between lines of both the series is 4b, while the separation between the exciting line, which is the undisplaced one, and first of each of the anti-Stokes and Stokes lines is 6b. The intensities of the Raman lines reflect the population of the rotational levels. As the initial state of anti-Stokes lines is higher in energy than that of the corresponding Stokes lines, the anti-Stokes lines are correspondingly weaker. This effect is small as the rotational energy levels are closely spaced except in light molecules. Vibrational Raman spectra. In simple harmonic oscillator model of a diatomic molecule, the energy levels are given by G nu is equal to omega nu plus 1 by 2. The selection rules for vibrational Raman spectra are delta nu is equal to plus minus 1. The vibrational transitions are observed at nu vibrational is equal to G prime nu minus G double prime nu is equal to G nu plus 1 minus G nu is equal to nu omega nu plus 3 by 2 minus omega nu plus 1 by 2 is equal to omega. Therefore, the Stokes and anti-Stokes components are obtained that are shifted by frequency E by h from Rayleigh line. Most of the molecules are in the lowest vibrational state at normal temperature and few are in the excited vibrational states. The intensity of the Stokes lines corresponding to transition 0 to 1 is thus much greater than that of 1 to 0 transition. The separation between the lowest vibration levels is so large that only the Stokes lines are observed at normal temperature in the diatomic molecules. The potential is not that of simple harmonic oscillator. The non-harmonicity of the vibrational potential causes the spacing between the vibration levels not to be constant. Thus, the occurrence of separated Stokes lines originates from different vibrational levels. Vibrational rotational Raman spectra. For a given vibrational band, nu is equal to nu naught plus b prime nu j prime plus 1 minus b double prime nu j double prime plus 1. Here nu prime is the frequency of pure vibrational transition without taking into account the rotation. The selection rules for vibrating rotator are those of an harmonic oscillator and the rotator, that is delta nu is equal to plus minus 1 plus minus 2 and so on, and delta j is equal to 0 plus minus 2, and for j prime is equal to j double prime plus 2 is equal to j plus 2, which is S branch. From the above equation, these equations can be written as: for j prime is equal to j double prime minus 2 is equal to j minus 2, this is O branch. So, frequency for the O branch is equal to nu 0 plus b prime nu j minus 2 j minus 1 minus b double prime nu j into j plus 1. This can be further expanded is equal to nu 0 plus 6b prime nu plus 3b nu minus b double prime nu j plus b prime nu minus b double prime nu j2, where j is equal to 2, 3, etc. And writing j prime is equal to j double prime is equal to j for Q branch, the expression can be written as. The figure depicts the rotational transitions accompanying a vibrational transition in a Raman spectra. The figure shows the corresponding j values 0 to 3, nu double prime and nu prime, again from j values 0 to 3. For vibrational transition 0 to 1, the difference between b nu prime and b nu double prime is very small. Therefore, b nu prime is equal to b nu double prime is equal to b. So, nu s depending upon j is equal to nu naught plus 4bj plus 6b, which is equal to nu naught minus 4bj plus 2b, and nu cube is equal to nu naught. Therefore, lines of Q branch are very close to one another and are not separately observed. This gives rise to an intense line at nu naught at shorter wavelength side. The separation of the first S0 and the first O2 is 12b. The S branch occurs at higher frequency and O branch is at lower side of the frequency of Q branch. The lines of S and O branches are very much weak. They form a series similar to R and P branches of infrared bands, except that the line separation is twice as large. The method of combination differences is used to obtain the value of b nu prime and b nu double prime. So, delta 4
double prime Fj is equal to nu Sj minus 2 minus nu naught j plus 2 is equal to 8 b nu double prime j plus 1 by 2, which is equal to nu Sj minus nu naught j is equal to 8 b prime j plus 1 by 2. Graphs of delta 4 Fj versus j plus 1 by 2 and delta 4 double prime Fj versus j plus 1 by 2 gives straight line with slopes 8 b nu prime and 8 b nu double prime respectively.
Intensity alteration in Raman spectra. Transitions between only even J rotational levels are observed, while transitions between odd J rotational levels are missing for Raman spectra of some molecules. However, there is an alteration in intensity of the adjacent lines in some molecules. The intensity of transitions between odd J value rotational levels is 3 times stronger than that between even J value rotational levels in case of Raman spectra of hydrogen molecule. This is understood on the basis of the Pauli principle, because for homonuclear molecules, the states that can be occupied and the transitions that are allowed are restricted by the symmetry requirement. In case of the integral nuclear spins 0, 1, 2, etc., the complete wave function of the molecule must be symmetric with respect to exchange of labels of two identical nuclei, while for half integral nuclear spin, the wave function must be antisymmetric in an exchange of the labels of the two nuclei, and these are identical fermions.
The total wave function psi of the molecule is psi is equal to psi e, psi nu, psi r, psi ns, neglecting the small interactions between the modes associated with the electronic, vibrational, rotational and nuclear spin behavior of the molecule. Here psi e, psi nu and psi r are the electronic, vibrational and rotational wave functions, while psi ns is the nuclear spin wave function. Now psi e and psi nu are symmetric in an exchange of the labels of the two nuclei. The symmetry of the wave function psi is governed by the symmetry properties of the product psi r, psi ns. For I having half integral value, psi and hence psi r, psi ns must be antisymmetric in nuclear label exchange, and thus if psi r is symmetric, psi ns must be antisymmetric. Considering the hydrogen molecule, spin of hydrogen nuclei is half, which is corresponding to fermion. So psi must be antisymmetric with respect to the interchange of nuclei. The psi r may be symmetric or antisymmetric depending upon whether J is even or odd. And for I is equal to half, ml takes the values plus half or minus half. The nuclear spin wave function psi ns is written as or corresponding to ml is equal to plus half or minus half respectively. Both the hydrogen nuclei labeled 1 and 2 can have either or nuclear wave function. There are 4 possible forms of psi ns for the molecule as a whole. Psi ns is equal to alpha 1 alpha 2 beta 1 beta 2 alpha 1 beta 2 beta 1 alpha 2. Alpha 1 alpha 2 and beta 1 and beta 2 are symmetric with respect to interchange of 1 and 2, while alpha 1 beta 2 and beta 1 alpha 2 are neither symmetric nor antisymmetric. The linear combination of alpha 1 beta 2 and alpha 2 beta 1 can be made symmetric or antisymmetric. The linear combinations are 1 by root 2 alpha 1 alpha 2 minus beta 1 beta 2 and 1 by root 2 alpha 1 alpha 2 plus beta 1 beta 2. These are antisymmetric and symmetric respectively. Thus there are 3 symmetric and 1 antisymmetric psi ns. In order for psi r, psi ns to be always antisymmetric for hydrogen molecule, the single antisymmetric psi ns is associated between even J value, while 3 symmetric psi ns are associated with odd J value. Thus transitions between odd J rotational levels are 3 times stronger than those between even J rotational levels.
Consider an example of carbon dioxide molecule which is linear and carbon atom is at the center of gravity of the molecule. Rotation about center of gravity involves only oxygen atoms and carbon doesn't move. The nuclei of oxygen O16 atom have a nuclear spin I is equal to 0. Particle with integral spins obey Bose-Einstein statistics, and according to Pauli principle, psi must be symmetric with respect to the interchange of the particle. Labeling, here we talk about the oxygen nuclei. The electronic wave function psi E is symmetric with respect to interchange of oxygen nuclei, since nothing changes in the interchange of the nuclei. The psi R is symmetric with respect to the interchange of the oxygen nuclei. The symmetry of psi R depends on the value of J. As spin I is equal to 0, therefore there is no nuclear spin function and hence ignored. In order for psi to be symmetric with respect to interchange of oxygen atoms, the psi R must be symmetric as psi E and psi nu are symmetric. Therefore, only the states for even J exist and odd J states are missing. That is, only even J states are populated. Hence, transitions between even J value rotational levels can take place and transitions between odd J value rotation levels are missing. Thus, in Raman spectra of carbon dioxide, everywhere line is missing.
In general case, the number of antisymmetric spin states to the number of symmetric spin states determine the relative intensity of rotational lines. It is shown that the ratio of antisymmetric states to symmetric spin states gives the ratio of strong and weak lines if two nuclei of homonuclear molecule each having spin I, then R is equal to I plus 1 by I for fermions and R is equal to I by I plus 1 for bosons. Infrared spectroscopy. There are three regions, the near, mid and far infrared in the infrared portion of the electromagnetic spectrum. The higher energy near IR, that is 14,000 to 4,000 centimeter inverse, corresponding to 0.8 to 2.5 micrometer wavelength, can excite overtone or harmonic vibrations. The mid infrared, that is 4,000 to 400 centimeter inverse, 2.5 to 25 micrometer, is used to study the fundamental vibrations and associated rotational vibrational structure. The far infrared, that is 400 to 10 centimeter inverse, corresponding to 25 to 1000 micrometer, lying adjacent to the microwave region, has low energy and is used for rotational spectroscopy. Infrared spectroscopy is based on the fact that molecules absorb frequencies that are characteristic of their structure. These absorptions occur at resonant frequencies, that means the frequency of the absorbed radiation matches the vibrational frequency.
The energies are affected by the shape of the molecular potential energy surfaces, the masses of the atoms and associated vibronic coupling. In Born-Oppenheimer and harmonic approximations, that is when the molecular Hamiltonian corresponding to the electronic ground state can be approximated by a harmonic oscillator in the neighborhood of the equilibrium molecular geometry, the resonant frequencies are associated with the normal modes corresponding to the molecular electronic ground state potential energy surface. The resonant frequencies are also related to the strength of the bond and the mass of the atoms at either end of it. Thus, the frequencies of the vibrations are associated with a particular normal mode of motion and a particular bond type. Number of vibrational modes. In IR active sample, the vibrational mode must be associated with changes in the dipole moment. However, a permanent dipole is not necessary, as the requirement is only for a change in dipole moment. A molecule can vibrate in many ways and each way is called a vibrational mode. consider a molecule with n number of atoms, then linear molecules has 3n minus 5 degrees of vibrational modes, while the nonlinear molecules have 3n minus 6 degrees of vibrational modes or vibrational degrees of freedom. So, for example, water molecule H2O is a nonlinear molecule for which 3 into 3 minus 6 is equal to 3 degrees of vibrational freedom or the modes occur. As simple diatomic molecules have only one bond, there is only one vibrational bond. In case of the symmetrical molecule like nitrogen, the band is not observed in the IR spectrum but found in the Raman spectrum. So, asymmetrical diatomic molecules like CO absorb in the IR spectrum. As more complex molecules have many bonds, so their vibrational spectra are also more complex, or the big molecules have many peaks in their IR spectra.
The atoms in a CH2X2 group, where X represents any other atom, can vibrate in 9 different ways. 6 of these vibrations involve only the CH2 portion. Symmetric and antisymmetric stretching, scissoring, rocking, wagging and twisting. Structures that do not have the two additional X groups attached have fewer modes because some modes are defined by specific relationships to those other attached groups. For example, in water, the rocking, wagging and twisting modes do not exist because these types of motions of the hydrogen represent simple rotation of the whole molecule rather than vibrations within it. The simplest and most important IR bands arise from the normal modes corresponding to the simplest distortions of the molecule. In some cases, overtone bands are observed. These bands arise from the absorption of a photon that leads to a doubly excited vibrational state. Practical IR spectroscopy. The infrared spectrum of a sample is recorded by passing a beam of infrared light through the sample. When the frequency of the IR is the same as vibrational frequency of a bond or collection of bonds, absorption occurs. Examination of the transmitted light reveals how much energy was absorbed at each frequency or the wavelength. Thus, measurement can be achieved by scanning the wavelength range using a monochromator. Alternatively, the entire wavelength range is measured using a Fourier transform instrument, and then a transmittance or absorbance spectrum is generated using a dedicated procedure. This technique is commonly used for analyzing samples with covalent bonds. Simple spectra are obtained from samples with few IR active bonds and high levels of purity. More complex molecular structures lead to more absorption bands and more complex spectra.
Uses and applications. Infrared spectroscopy is a simple and reliable technique widely used in both organic and inorganic chemistry, in research and industry. It is used in quality control, dynamic measurements and monitoring applications such as the long-term unattended measurement of CO2 concentrations in greenhouses and growth chambers by infrared gas analyzers. It is also used in forensic analysis in both criminal and civil cases. For example, in identifying polymer degradation, it can be used in determining the blood alcohol content of a suspected drunk driver. IR spectroscopy has been successfully used in analysis and identification of pigments in paintings and other art objects such as illuminated manuscripts. A useful way of analyzing solid samples without the need of cutting the samples uses ATR, that means attenuated total reflectance spectroscopy. Using this approach, samples are pressed against the face of a single crystal. The infrared radiation passes through the crystal and only interacts with the sample at the interface between the two materials. With increasing technology in computer filtering and manipulation of the results, samples in solution can now be measured accurately water produces a broad absorbance across the range of interest and thus renders the spectra unreadable without this computer treatment. Some instruments will also automatically tell you what substance is being measured from the store of thousands of reference spectra held in storage. And infrared spectroscopy is also useful in measuring the degree of polymerization in polymer manufacture. Changes in the character or quantity of a particular bond are assessed by measuring at a specific frequency over the time. Modern research instruments can take infrared measurements across the range of interest as frequently as 32 times a second. This can be done whilst simultaneously measurements are made using other techniques. So this makes the observations of chemical reactions and processes quicker and more accurate. Infrared spectroscopy has also been successfully utilized in the field of semiconductor microelectronics. For example, this can be applied to semiconductors like silicon, gallium arsenide, gallium nitride, zinc selenide, amorphous silicon, silicon nitride, etc.
Another important application of infrared spectroscopy is in the food industry to measure the concentration of various compounds in different food products. The instruments are now small and can be transported even for use in field trials. Infrared spectroscopy is also used in gas leak detection devices such as the DP-IR ICGAs. These devices detect hydrocarbon gas leaks in the transportation of natural gas and crude oil. In February 2014, NASA announced a greatly upgraded database based on IR spectroscopy for tracking polycyclic aromatic hydrocarbons in the universe. According to scientists, more than 20% of the carbon in the universe may be associated with these hydrocarbons, possible starting materials for the formation of life. These polyhydrocarbons seem to have been formed shortly after the Big Bang. They are widespread throughout the universe and are associated with new stars and exoplanets. Recent developments include a miniature IR spectrometer that is linked to a cloud-based database and suitable for personal everyday use, and NIR spectroscopic chips that can be embedded in smartphones and various gadgets.
Infrared and Raman spectroscopy, if we come to the difference of these two, though infrared and Raman are two similar spectroscopic techniques, but they differ as the photons interact with molecules and induce transitions among the available energy levels. These transitions result in the emission of photons with various wavelengths. So the photons emitted due to transitions between the vibrational energy levels of a molecule are detected with two spectroscopic techniques. One is infrared, the other is Raman spectroscopy. The difference lies in the nature of the molecular transitions taking place. For a transition to be Raman active, there is a change in the polarizability of the sample during the vibration. This means that the electron cloud of the molecule undergoes positional change, while for an IR detectable transition, the molecule undergoes dipole moment change during vibration. Therefore, one cannot observe any IR absorption lines in case of symmetrical molecule, for example, oxygen, as the molecule cannot change its dipole moment. The molecules with a strong dipole moment are hard to polarize. The Raman technique uses a monochromatic beam or a laser in the visible, near infrared or near ultraviolet range of the electromagnetic spectrum as an excitation source. In IR spectroscopy, a monochromatic beam is used in the infrared region of the electromagnetic spectrum. So in order to observe all the observations of the absorption lines within a specific range of the infrared region, the wavelength increases or decreases over the time. Another difference is observed in the resulting spectra. The IR technique shows irregular absorbance or the transmittance lines depending on the material under test. The Raman spectrum mainly comprises the elastic scattered light line, that is Rayleigh line, and two equally distant lines, stalks and anti-stalks, with the second being quite weak and difficult to detect. So it is to note that Raman technique requires high stability laser sources and sensitive amplification equipment to detect the weak signal.
Raman and IR active modes for CO2. As it is shown that vibrational Raman shift in Raman spectrum of the diatomic molecule is same as that of the wave number of the fundamental vibration band in NIR spectrum. It is because of the fact that fundamental infrared absorption band of diatomic molecule is observed as a vibrational transition which is nu is equal to 0 to nu is equal to 1, that is same as of vibrational Stokes Raman band. The figure depicts the stretching in carbon dioxide molecule CO2, where symmetrical stretching is there, no change in dipole moment, therefore IR inactive. If there is change in polarizability, therefore it is Raman active. While the antisymmetric or asymmetrical stretch, there is change in dipole moment, therefore IR active, but Raman inactive. In plane bending and out of the plane bending, the deformation vibrations of CO2 are degenerate and appear at the same region in the IR spectrum of CO2. There is no change in polarizability, therefore these vibrations are Raman inactive. There are certain similarities. Both are common vibrational spectroscopy useful for assessing molecular motion and fingerprinting species. Both work on the basis of inelastic scattering of a monochromatic excitation of source. The routine energy range is 200 to 4000 centimeter inverse. If we talk about the difference between IR spectra and Raman spectra is due to the scattering of light by the vibrating molecules, while IR is the result of absorption of light by vibrating molecules. The vibration is Raman active if it causes a change in polarizability, while the vibration is IR active if there is change in dipole moment. The molecules need not possess a permanent dipole moment in case of Raman spectra. The vibration concerned should have a change in dipole moment due to that vibration in case of IR spectra. Water can be used as a solvent for Raman, while water cannot be used due to its intense absorption of IR. Sample preparation is not very elaborative. It can be of any state while performing the Raman spectra, whereas sample preparation is elaborate. Gaseous samples can rarely be used in case of IR spectra. Raman spectra gives an indication of covalent character in the molecule, while the IR gives an indication of ionic character in the molecule.
So, in this summarizing all this, what we have learnt is the Raman scattering, rotational Raman spectra, vibrational Raman spectra, rotational and vibrational Raman spectra, intensity alteration in Raman spectra, infrared spectroscopy, particularly the difference between IR spectroscopy and the Raman spectroscopy, Raman and IR active modes. So, thank you.